Hello.
Good evening, sir.
Hello, good evening. Yes.
Okay, I think I am only the person joined in the meeting, sir.
Yeah, right. I was waiting for people to join.
Okay, okay, sir.
Yeah. So we can actually get started with the session. Yeah, thanks for joining. It actually got scheduled over a short notice. So the notice actually just got posted today evening.
Yes, sir, yes, sir. Today only we got it, sir.
Yeah, right, right. Yeah, so thanks for joining. So do you have any questions to ask? So the your
No,
yeah.
sir,
Yeah.
I don't have any questions, sir. Actually, sir, you are only the providing the key, sir.
I was providing what?
So key and solution, sir.
So today's session I am actually uh, have like conducting for like a revision, and if anyone has any questions, any doubts, I can answer them. I will try to answer them. So if you have, so otherwise I have planned like revision through the some of the topics. So I can just
Okay, sir. I don't have any doubts. Only please explain me. Means assignment questions or similar questions only will be asked in the exam, no, sir.
yeah, I think so. Uh,
Okay, sir.
Okay, fine, thanks. So I think we'll just get started with the presentation then. So I will
Okay,
be
sir.
sharing my screen. Just hold on.
Okay, sir. No problem, sir. Yeah. You can share or you can send me the PPT also, sir. No problem, sir. I will read it, sir. Means because for only one person you have to explain, sir. One more person join. Oh no, no, you are only one.
So can you see my screen?
Yes, sir. I am able to see, sir.
Okay, fine. Yeah, so I'll just go through the PPT. Uh, so I have prepared some slides so that it will help you to revise some of the topics. Uh, so week wise, I have basically listed down what are the topics. So first week contents were basically fundamentals of vibration, uh, like topics like harmonic motion. So what is the definition of harmonic motion? Then how do we add two different harmonic motions? And when we have like harmonic motions whose frequency is very close, then we see the phenomenon of beats, and what is the frequency of beats. So all those concepts were covered. Then uh, Fourier series and harmonic analysis, that was also covered as a part of this uh, this week's first week's topic, and the general procedure for vibration analysis. So we'll just go over the Fourier series. So if we have any periodic function, let us say x of t, uh, so then we can express it as a Fourier series, or basically a series, basically a sum of sine and cosine functions with different frequencies. So for being able to write x of t as a like to represent it as a Fourier series, the requirement is that this function x of t should be periodic. So given that it is periodic, then we can write the Fourier series like the way it is shown over here. It is a sum of cosine and sine functions of different frequencies. So now on the right hand side we can see this figure over here. So the original function is uh, like the way it's like a sawtooth kind of a sawtooth wave. So then by using different like one term approximation or two term approximation or three terms, so considering different number of terms for writing the Fourier series, we can see how we can improve the approximation of this, basically how closely we can approximate this function by using like finite number of terms. So as we go on increasing the number of terms, we see that the approximation of the function becomes better and better. So then to find out the values of the coefficients an, bn and a0, we basically use the property of orthogonality of sine and cosine functions. Basically, if we multiply let us say cos n omega t into cos m omega t and integrate it over its period 0 to 2 pi by omega, then the integral will be 0 if m is not equal to n, and it will be non-zero if m is equal to n. So using that same property, we basically use it to find out the value of these coefficients an and bn. So we multiply the whole Fourier series by cos n omega t and integrate it over 0 to 2 pi by omega, then we get the value of an. And if we multiply the entire Fourier series by sin n omega t and integrate it over 0 to 2 pi by omega, we can get the values of the coefficient of like basically bn. And depending on whether we have an odd periodic function or an even periodic function, so an and bn will be like vary accordingly. So if we have an even periodic function, then because cos x or is basically, or cos of omega t is it's an even function. So an even function into an even function will result in another even function, whereas an even function into an odd function, so sin x is an odd function, so here x of t will be even and sin n omega t will be an odd function. So x of t into sin n omega t will be a odd function. So basically bn will become 0 for when the function x of t is even, and when x of t is an odd function, then the terms an will become 0 because x of t into cos n omega t will become a odd function. So that is the general property of the sine and cosine functions and how it is basically used in the Fourier series. Now we'll move on to the general procedure for vibration analysis. So before that, I just wanted to know, so I think someone else also joined. So are there any questions, any doubts that you wanted to ask? So I am basically just going through some of the topics as a revision in this session. So if you have any specific doubts or any questions to ask, you can ask right now itself. Any doubts, any questions? Fine, I think we can just continue with the presentation. So the general procedure for vibration analysis has some basic steps. So the first step is basically mathematical modeling. So uh, so in mathematical modeling we basically try to capture some of the properties of the system. So in the context of vibration analysis, it's mainly mass, stiffness and damping characteristics. So depending on what we are interested in, so we will uh, basically define whatever model that is just good enough for our purpose. So the uh, complicate like the level of complication of the model, or basically the model fidelity, will be decided on based on what we are interested in and what is the extent of accuracy that we really require uh, for the model. And so basically we use our engineering judgment to determine what model is good enough. So for example, if we want to model the car, so then we can just model the entire car body as a single lumped mass, which is mounted over on top of the wheels with using a spring, which is, so the spring can be represented as basically the suspension, and the wheel will become again, so we can lump all the four wheels together into a single mass, and then we can have a single spring which represents all the suspensions, like the suspension for all the four wheels. And then we have the what is called as the quarter car model, which we have studied earlier. So then that is that may be just good enough for simple studies where we are basically trying to where we assume that all the four wheels are always in contact with the road and are moving like the displacement of all the four wheels is the same, the suspension stiffness is the same for all the so things like that. So we can basically like if we now are interested in how the displacement of the front wheels and rear wheels is, it changes as the let us say a car goes over a bump, then we will have to consider a model in which the front wheels and the rear wheels will be modeled separately. So so that is how, like based on whatever we are interested in, we will decide what model has to be used. So the models may be linear or non-linear depending on the variation of the characteristics. So generally linear models we can use it for simple studies where we just want some quick solution and idea of just for some basic decision making. So linear models may be suitable. So the next step in vibration analysis is basically to derive the governing differential equations for the system, or basically the equations of motion. So so to get the equations of motion there may be various methods. So one of the common methods that is used is basically from dynamics. So we can just apply the Newton's second law, uh, and using that we can get the equations of motion. Or there are some energy based methods where we find out the kinetic energy and the potential energy of the system, and use the fact that the overall energy is conserved, and so we differentiate the total energy with respect to time and equate it to zero, and based on that we can get the equation of motion. Then the next step is like having basically once we get the governing differential equation, then the next step is to basically solve the governing equations. So there are different various methods that we can use to solve the governing equations. So they may be analytical or numerical. So if the differential equation is simple enough, or like ordinary differential equations with constant coefficients, then we can easily solve it analytically. Or if the differential equation is such that it is difficult to solve analytically, then we have to resort to numerical methods. Now having obtained the solution, the next step is to basically interpret the results. Basically so when we start off with a certain study and we were expecting something, and whatever the result shows, so the results whatever that they show, they may either be aligned with whatever you had expected or something different than what you had expected. So basically this is the general procedure for vibration analysis. So in the next week we had the content related to free vibrations of single degrees of freedom systems. So degree of freedom is an important concept in the context of vibration analysis, or for that matter any dynamical system. So degree of freedom is basically the number of independent variables that are required to describe the behavior of the system. So here single degree of freedom system means we just have one independent variable that describes the motion of the system. So in this week we had topics related to undamped free vibration uh, and damped free vibration. Some energy methods were also
Sir,
covered.
your screen is not visible, sir. Hello, sir.
Yeah, I'm just sharing my screen again.
Sir, and also one request is that please share that your PPT, sir. I will go through one, sir, because I mean, sir, I have some work and also I have to prepare one more exam like SPM also is there, sir.
Yeah, sure. I will be sharing this presentation.
Oh, okay, sir.
Yeah, so you will get it from the course website.
Okay, sir. Okay, sir. That will be good, sir, because so that I'll just quickly review that thing, sir.
Yeah.
Okay, sir. Yeah, you can continue, or you can means I think I am also only the person, sir. Maybe
Yeah, I
as
will
your
be
wish,
just
sir.
going through the entire presentation, and I will be recording my presentation. So it's already being recorded. So I will. Uh, so once the recording is done, I will post it on the course website, and also the presentation will also be available to you. You can access it like the both the recording as well as the presentation slides, and so you
Yes,
can
sir.
review it later. If you have any questions, you can also so you can use this session for mainly for asking questions.
Yes, sir. Yes, sir. Okay, sir. No problem, sir. If I have any doubt, I will ask you. Otherwise, no problem, sir. You please continue, sir.
Yeah.
Please continue, sir. Okay. Thank you, sir.
Yeah, so in this week's content, for second week we had single degree of freedom systems. We studied uh, undamped free vibrations, damped free vibrations. Um, Particularly, we studied viscously damped systems and logarithmic decrement, and we also studied Coulomb damping and different types of damping. So, so in the overall subject of vibrations, if we understand single degree of freedom systems, the concepts related to single degree of freedom systems, and the methodology, general methodology for vibration analysis, so then that like understanding single degree of freedom systems itself is very important. And once you understand the concepts related to single degree of freedom systems, it will be easy to understand the concepts related to 2 degree of freedom or even multi degree of freedom systems, because the similar kind of methodologies will apply to higher degree of freedom systems. So I will be explaining the concepts of single degree of freedom systems in slightly detail, so that it's be better for you to understand them clearly. And once you understand these concepts clearly, it will be easy for you to follow the concepts related to 2 degree of freedom or multi degree of freedom systems. So if we consider undamped free vibrations, then we will basically consider a single spring mass system. So let us say m is the mass of the system and k is the stiffness of the spring. So then we have mx double dot plus kx is equal to 0. That is the general differential equation of this system. So now to solve the this differential equation, we assume a certain solution of the form x of t is c into e to the power st. So then we substitute this solution into the differential equation. So we get c into the bracket ms square plus k is equal to 0. So now we have to solve for so to solve this differential equation, we need to know the value of c as well as s. So for in this equation, assuming that c is not equal to 0, which will basically mean that it's a non-trivial solution, so then ms square plus k is equal to 0. So then that will be a quadratic equation in s. So basically we get that s is equal to plus or minus root minus k by m, or plus or minus I root of k by m, or I omega n. So where omega n is square root of k by m. And so then we can write down the general solution of this differential equation in this form. So as c1 e to the power I omega n t plus c2 into e to the power minus I omega n t. Or alternatively, we can use the identity that e to the power I omega n t is cos omega n t plus I sin omega n t, and we can also alternatively write down the expression for the general solution like a1 cos omega n t plus a2 sin omega n t. Both are equivalent. So we can find out the values of c1 and c2 or a1 and a2 using the initial conditions. So the initial conditions can be basically the initial displacement and the initial velocity. So we need two initial conditions to determine the values of the two unknown constants, c1 and c2 or a1 and a2, whatever we use. So then using the initial so considering that the initial conditions are known, then we can write down the final solution like in this form in terms of the values of the initial conditions. Now we can also write down the same solution a1 cos omega n t plus a2 sin omega n t in this form as x of t is a cos omega n t minus phi. So instead of having two constants as the amplitudes a1 and a2, we can have a single amplitude and a phase as the constants that characterize the motion. So we can determine the amplitude from the initial conditions using these equations which are given over here, and also the value of the phase angle we can find out using these equations which are given over here. Alternatively, we can also write down the solution in the form of a naught sin omega n t plus phi naught. So instead of cos, we can just represent it as a sine function, and then we can basically write down the expressions for the amplitude and the phase angle in this case. So those are as per whatever expressions that are given here in this slide. Now so basically the solution in the form of x is equal to a cos omega n t minus phi or a sin omega n t plus phi, whatever. So those are basically harmonic oscillations, and here in this figure it is shown as projection of simple harmonic motion. So if we have a particle that moves around a circle with a constant angular velocity omega n, then the phasor or basically the vector will be which basically describes the position of that a particle at any time t. It will be basically this vector which is shown over here, a vector. So it will be rotating about the center of the circle and at a constant angular velocity omega n. So if we find out the projection of this motion on the x-axis or y-axis. Then using that we will basically either get cos omega n t minus phi or sin omega n t minus phi, depending on which axis we are projecting this uh, uh, like depending on which axis we are projecting our circular motion. So simple harmonic motion is basically projection of circular motion onto one of the axis, horizontal axis. So now the next concept is damped free vibration. So like if we consider a spring mass and damper system, which is shown over here, and the free body diagram of the system is also shown over here. So then the differential equation will be it can be written in this form: mx double dot plus cx dot plus kx is equal to 0. And if we assume a general solution of the form c e to the power st and substitute in the differential equation, then we basically get another characteristic equation in terms of s, and we can solve this characteristic equation. Basically it's a quadratic equation in s, and we can determine the roots of this quadratic equation, and so those can be found out here as given over here. And then we can find out basically write down the general solution of this differential equation as c1 e to the power s1t plus c2 into e to the power s2t, where s1 and s2 are basically the two roots of this quadratic equation or characteristic equation. And depending on the values of stiffness, mass and damping ratio or damping factor, basically that there will be different regimes or different kind of motions that are possible in the damped free vibrations. So to decide what kind of the motion uh, that would result, so we basically find out the value of the critical damping, which will be basically the deciding factor on which decides the regime of the motion. So if the damping value is greater than the critical damping value, then we will get two real and distinct roots, s1 and s2, and then that will result in a certain kind of motion, we will see that. And if the value is less than the critical damping value, then it will result in another certain kind of motion. Then the roots s1 and s2 will be complex conjugate roots, and then if the damping is exactly equal to the critical damping value, then it will result in a critically damped motion. So which is, we will see all the different cases that are possible. So the first case is if the damping value is less than the critical damping, so then we will get complex conjugate roots s1 and s2, and we can write the general solution for the differential equation in this form. Uh, Hello. Hi. So I think someone joined. So basically in today's session I am basically just going through the entire some of the topics in the syllabus as a revision. So if you have any questions you can ask. I will be just going through the presentation for this session.
Sir, actually, the week 7 and week 8
Yeah.
assignment solutions not posted in the group.
Okay. Yeah, I think those. So I think they will be posted soon by the TAs.
No, actually, Sunday is the exam. This Sunday.
Yeah, I know. But I think because of some reason it might have got delayed. I'm not sure because I'm not exactly part of the
Yeah, yeah, I can understand.
Yeah, yeah, sir. Yeah, so if there are any other questions or concerns, so you can ask them, or otherwise I'll just continue with the presentation.
No, no, actually, only that doubt only. When we'll get assignment solutions like. Otherwise, it is going well.
Okay.
This course is going well.
Okay.
No other issues.
Okay. Have you gone through any of the live session videos?
Previous video I have gone through. It's good.
Okay.
Recorded video only. I have not attended.
Yeah, yeah, right. Uh, so I have been posting videos every week for like these live sessions. So yeah, hopefully maybe more people should join, but yeah, at least you can watch the recorded session. So I think I'll just continue with my presentation. So you
Yeah,
can,
yeah, yeah.
so you can,
Yes.
yeah. Yeah, so if we were basically looking at the underdamped case, so here we have the damping is like value is less than the critical damping, and then we can write down the general solution of this differential equation like this, and then based on the initial conditions we can basically get the values of the constant c1 prime and c2 prime, or c1 and c2, whatever we use, and then this is the final form of the solution. So I don't think you need to memorize all these uh, basically equations or formulae. So you can just make a note of what is the approach, and then follow that approach for any case. So I don't think you need to memorize the final values of the displacement as a function of the initial conditions. So this is how the damped free vibration, uh, like this is the general nature. So the amplitude of the motion goes on decaying exponentially as the vibration progresses, and we have the oscillations will be at the damped natural frequency omega d, uh, which is basically given by this equation. The next case is basically critically damped systems where the damping value is exactly equal to the critical damping value. So then there will be no oscillations in the system because there will be two equal roots for the characteristic equation. So uh, the motion will be like it will just go up and then exponentially decrease depending so like this is like depending on what will be the initial conditions, but the general form of the displacement will be like this, something like this. Then we have the next case as overdamped systems. So if the damping value is greater than the critical damping value, then there will be two real and distinct roots for the characteristic equation S1 and S2, and the general solution for the differential equation will look like something like this. So the figure over here shows the comparison of the different uh, kinds of motion that like will be observed depending on the damping ratio, or basically the ratio of the damping to the critical damping value. And yeah, so the time period will also change depending on whether uh, the value of zeta, so it will slightly alter the natural frequency of the vibrations. So in basically in case of overdamped and critically damped systems, so there will be no oscillations. it will just rise up to a certain value and then just keep on exponentially decreasing. So another concept which we have is logarithmic decrement. It's basically just a tool to find out the value. So considering that we have been given the reduction factor in the amplitude in successive cycles, so then that, let us say we have been given delta, which is the ratio of uh, or natural log of the ratio of the successive amplitudes. Then we can derive an expression for this factor delta in terms of the damping value zeta. So if the damping value is very small, we can approximate it to be nearly 2 pi zeta, and basically we can use it to find out the so it's like if we perform an experiment and observe the amplitudes and its reduction over, let us say, 10 cycles, and then note the reduction in the amplitude and find out its natural log, and then we can use it to find out the estimate basically the damping present in the system. So the next topic is basically forced vibration of single degree of freedom systems. So in that, so if we consider, let us say, any general uh, damped system, so that is subjected to some forced vibration f of t force as a function of time. So then mx double dot plus cx dot plus kx, that is basically the general differential equation of the system. So let us now, if we consider like undamped systems, so then the differential equation will look something like this. If we consider that the force f of t varies as f naught cos omega t, then as we change the frequency of the oscillations of the force, or basically the harmonically exciting force, its frequency as it changes, then this is basically the variation of the magnification factor, or basically the steady state amplitude x, how it varies with respect to the static deflection uh, as a function of the frequency omega. So as omega, when it is less than omega n, so then the magnification factor will increase, and it will be infinite when the frequency of the basically the exciting frequency, when it equals to the natural frequency of the system, then that will result in resonance, or the magnification factor is infinite, because this is an undamped system. So now similarly, if we consider a damped free vibration, so this is the general expression for the magnification factor for the for a damped free vibrations, damped forced vibration, and also the phase difference in terms of the frequency ratio and the damping ratio. So zeta is basically the damping ratio, and r is basically the frequency ratio, omega by omega n, and this is the equation for the steady state amplitude value. So we can see that in this plot how the magnification factor m, which is x by delta static, how it varies with respect to the frequency ratio. So when the frequency ratio is close to 1, then we can see that there is a peak close to the value of when the frequency ratios, or basically when the excitation frequency is close to the natural frequency, then we see that there is a peak in the magnification factor, or there is resonance. So in the fourth week, the topics related to damping, or like basically Coulomb damping, structural damping, and the concepts of vibration, isolation, and force transmissibility and motion transmissibility, they were covered. So I will not be going into the details of those topics. Then I will move on to the week 5 topics, basically transducers and vibration pickup. So transducer is basically any uh, device which can convert mechanical motion into an electrical signal, and vice versa. So piezoelectrics are materials are an example of transducer. So when mechanical pressure is applied to a piezoelectric crystal, then it will result in the creation of opposite charges, positive and negative charges, or there is a potential difference, and that will result in a flow of current if it is connected in an electrical circuit. So uh, basically mechanical pressure gives rise to it generates an electrical signal which is proportional to the mechanical pressure. So this property is used in making sensors or basically vibration, so which can be used as vibration measurement devices like vibrometer or accelerometer or velocity pickup. So vibrometer is something which measures basically it captures the signal which is proportional to the displacement that we are interested in. Accelerometer is basically measures the acceleration, or velocity or pickup or velometer will measure the velocity. So then let us say if we have this system which is shown over here, which is mass spring and damper. So it is mounted on top of this surface which is moving at oscillating at, let us say at as y of t, and this mass m, which is basically the this is basically the vibration measurement device, and that mass is oscillating at as given by x of t. So whatever we will be measuring will be the relative displacement z, which is x minus y, and let us say if y is undergoing a harmonic motion y sin omega t, then we can write down the differential equation for this system and it will look something like this. And assuming that there is a harmonic motion for y, then this equation will look something like this, where we have m omega square y sin omega t, which acts like a excitation force. And if we assume that a general solution of this form for z, so we will get basically z in terms of y, or basically the amplitude, and we get basically the expression of how z by y changes as a function of the frequency ratio and the damping ratio. So depending on what is the frequency range in which we are operating in, so here z by y will be nearly equal to 1 when omega by omega n is greater than 3. So that is generally the range in which we can use this system as a vibrometer. So it's the relative displacement that will be measured, it will be nearly same as the displacement of the y, whereas in the where the natural frequency of this system is very high, or basically the let us say if we have a piezoelectric accelerometer, so it will have a very high natural frequency. So the frequency ratio on of basically the system which on top of which it will be mounted, it will have a frequency ratio which is very low. So in that range it will be effective as an accelerometer. So now in the next week or 6th week we studied 2 degree of freedom systems. So we studied the undamped free vibration and damped free vibration. And we also studied the forced vibration with harmonic excitation. So here in this in these 2 degree of freedom systems, So in our session we had seen that we had modeled a car as a 2 degree of freedom system. So here we have to apply the same kind of methodologies like the way we apply for single degree of freedom systems. We have to find out the equation of motion. For here now we have 2 degrees of freedom, so we have two masses, and we have to draw the free body diagrams for the masses, and then we derive the equation of motion. And now we can express the equation of motion in matrix form. So we will get mass matrix, damping matrix and stiffness matrix, and also the matrix for the forcing. So that will result in an equation of the form mz double dot plus cz dot plus kz is equal to f. So where m is the mass matrix, c is the damping matrix, and k is the stiffness matrix, and f is the vector, forcing vector. So then how do we solve this? So this method is also like for applicable for any system which is like ranging from single degree of freedom, like 2 degree of freedom, to any multi degree of freedom systems. So let us say we have a solution of the form z. So then the solution can be split up into two parts: solution to the homogeneous equation where the force vector is 0, and then the particular solution which is depending on the nature of the force F. So for that we assume, so for the homogeneous solution we assume a solution of the form v into e to the power lambda t, and then substitute in the differential equation, and then when we substitute we will get a characteristic equation in terms of lambda, which we can solve it to get the roots lambda, and then once we get the roots lambda, we can find out basically the determinant of the characteristic equation. So that will give us the characteristic equation, and it will have 4 roots. So let us say we call them as lambda 11, lambda 12, lambda 21, and lambda 22. So then we can write down the general solution for this homogeneous differential equation, and we will have 4 unknown constants. So they can be found out using the initial condition, and so corresponding to each lambda 11, lambda 12, lambda 21, and lambda 22, we will have eigenvectors which is corresponding to each lambda square value. So then let us say if we have a 2 degree of freedom system, so then we will have 2 eigenvectors. So so now to determine the particular solution, we will let us say if we assume that the force is sinusoidal, then we will substitute like the force vector in like this form. So it will have like a1 cos omega t plus a2 sin omega t, and b1 cos omega t and b2 sin omega t. So in that form, and then substitute it in the differential equation, and compare the coefficients of cos omega t and sin omega t on the left hand side and right hand side to find out the unknown constants. So that is how we will determine the particular solution. So we find out the homogeneous solution using the eigenvalues, and as a linear combination of the eigenvectors we write down the general solution for the homogeneous differential equation, and the particular solution we can find out using the method which was just described right now, and we combine them together and apply the initial conditions to get the unknown constants. So this is the general method which is applicable to 2 degree of freedom as well as any multi degree of freedom systems. So we saw the methods for of vibration analysis for multi-degree of freedom systems. So then we also had covered the concepts related to vibration absorber. So, in the 7th week, so we had studied we considered some problems related to critical speed of shafts. So the displacement of the shaft is given by uh, this expression in terms of omega and the natural frequency. So as the uh, frequency of the eccentric load it changes, then this is how the displacement of the shaft varies, and so the critical speed is when omega is equal to omega n. Now for vibration absorbers, we had seen that if we add basically a spring mass system to the original system, let us say if it is oscillating at close to its natural frequency, then we add a vibration absorber which is in the form of a spring mass system which has the same natural frequency as the original system. Then by adding a tuned vibration absorber, which is then it will provide another path for the kinetic energy to pass through, and then when the system is oscillating at the it's operating at the natural frequency, the vibration absorber will take away most of the kinetic energy and it will oscillate with high amplitudes and then reduce the amplitude of the oscillation of the original system. So that is the basic principle of the tuned vibration absorber. So it is basically used to reduce the vibration of the original system. So in our earlier presentation we had seen how the vibration absorber works. So in this figure which we have seen over here, so here we have uh, a peak when the system is working without a vibration absorber. So that results in very high amplitudes without vibration absorber, and when we add a vibration absorber, then we can see that how the amplitude has reduced significantly when it is operating at the natural frequency at 1 hertz. So the red curve is basically our original system, which is the mass m2, and the mass m1 is basically the vibration, represents the vibration absorber. So it takes away most of the kinetic energy by oscillating at high amplitudes. So that is the basic principle of the vibration absorber. And now we come to the last concept of multi-degree of freedom systems. So here the methodology which I described for 2 degree of freedom systems is the same. We solve it using the same methodology, so I won't be repeating it again. So that was it from my side as revision of the concepts. So I hope you find this presentation useful to revise all the concepts or most of the concepts related to which will be asked in the examination. So I wish you all the best for your exams. So thank you.